Okay, everybody, let's take a look at the pH scale. All right, so far we've looked at what acids and bases are. We looked at the definitions of acids and bases. We looked at conjugate acid-base pairs based on the Bronsted-Lowry definition. We talked about concentrations of hydrogens and hydroxides using the equilibrium of water. Now what we're going to do is we're going to take a look at the fact that when we were dealing with those reactions, think about what we did with those hydrogen concentration problems. Well, a lot of those concentrations of the hydrogen ion were really, really small. We had things like 1.2 times 10 to the minus fifth molar, and we had, 3.45 times 10 to the minus ninth molar. So we were constantly dealing with low concentrations of hydrogen ions. And the reason for this is that in pure water, the hydrogen ion concentration in pure water is equal to 1.0 times 10 to the minus 7 molar. So in pure water, we don't have very many hydrogen ions, so it doesn't take a lot of hydrogen ions to really throw off the concentration of hydrogen. And since we're constantly working in this really low, small scale all the time, we want to kind of change this and get rid of it because we don't want to keep dealing with those small numbers. Okay, so what scientists devised was what's known as the pH scale. Okay, so when we deal with the hydrogen ions, because they're unusually small, we're going to just change the magnitude of the numbers. We're just going to work with a whole different scale. Since we're dealing with scientific notation and it's always powers of 10, we're going to use a logarithmic scale that's based on 10. Now, if you've used logs in class in math, great. If not, don't worry about it. I'm going to show you what to do with logs. It's not a big deal. All you need to know is where the button is on your calculator. So we're going to use the pH is equal to what's called the negative log. P is what's called a mathematical operator. And in math, wherever you see the P, technically you're supposed to take the negative log. So what we're going to do is take our concentration of hydrogen ion and take the negative log to get the pH. So what we're going to do here is going to find the pH of pure water. Well, remember, pure water has a hydrogen concentration of 1.0 times 10 to the minus 7 molar. All right, so what I'm going to do to find pH is I'm going to take the negative log of that concentration of the hydrogen ion. It's going to take this concentration of hydrogen and plug it into my equation. So 1.0 times 10 to the minus 7. All right, so I can find the pH, and I can find that my pH is 7.00. All right, now you take the negative log, and how you do that in your calculator depends on if you have a graphing calculator, if you have the calculators I use in my class. What you do if you have the calculators in my class, the smaller ones, the non-graphing one, is you take this number, type it in using scientific notation, hit the log button, then hit the negative button. If you have a graphing calculator, put in the negative, put in the log, then put in your number, then hit enter or equal, and you'll end up with 7. If you try that and you don't get the number 7.00 like this, then it means you're making a mistake. Now, one word about logs. If you used them in math before and you were very confused as to what they are, here it is. It's really simple. The log is the number that's the 10 power. That's essentially what the pH or the log is. So anytime we do these problems, you can estimate what your pH is going to be by just looking at this number here. Don't worry about this number so much. Worry about this one here, because this is what's going to give us we're going to figure out our pH by using that. Okay? All right, so this is why in pure water our pH is 7. You remember before when we were comparing whether something is acidic or basic, we kept comparing hydrogen ions and we were comparing them to the hydroxide ion concentration. Well, that is really the idea. Is if the hydrogen ion is greater, then it's an acid. If the hydroxide is greater, it's a base. If they're equal, then it's neutral. That's still true. That's not going to change. We're just not going to keep focusing on the pH or the concentration of hydrogens. We're going to change it to the pH scale. And remember that at pure water, it was to the negative 7 power, so if hydrogen was greater, then we would say it was greater than that negative 7 power. Then it was an acid. If it was less than it was a base. So now we can just, instead of dealing with that big number in scientific notation, we can simply use pH now. It's a more convenient system once you kind of understand how to use it. So for our pH, there's a lot of things. Here's our pH scale. Now a lot of students think that it's a cutoff here, that the scale goes from 0 to 14. No, it can go beyond 14 and it can go below 0. There is no cutoff on the scale. Why do we say that it stops at 0 and it stops at 14? Why do a lot of teachers do that in the past? Because one, they don't really know the science, and two, Most substances we deal with in nature, like soap or milk or lemons or drain cleaners, typically are in that a range. You know, a lot of common substances you deal with don't really fall into that, outside of that range. So everyday things will fall between the 1 and 14, but for chemistry, I can get a strong enough acid that I could have a pH that's negative. That definitely can happen. And I can have a base that has a pH that is higher than 14. So our cutoff is that right here, that's 7. So anything that's above 7 on the pH scale is a base. Anything below 7 on the pH scale is considered an acid. Okay, so it's a little confusing. Why is it like that? If we're dealing with pH is equal to negative log and we're focusing on the hydrogen concentration, why is it that we have low pHs that we have an acid? Wouldn't it make sense that if our concentration of hydrogen were greater, that we would have a higher pH? I mean, I think that's what a lot of people instinctively think, but not really. And the reason why has to do with one little simple thing. It has to do with the fact that we are taking the negative log. We are flipping it upside down and inversing the scale. That's why our pHs that are low are acidic and pHs that are high are basic. We flip-flop the scale by putting the negative in there. Okay, so keep that in mind. The lower the acidity, the lower the pH, the more acidic it is. The lower the pH, the more acidic it is. Okay, all right. So we have also another scale. So we can take the negative log of just about anything we want. So we can have what's called a pOH scale. So just like we had a pH, we can have a pOH scale. So we can take negative log of just about whatever you want, not a big, we could take the negative log of, we could do a pKW. That would be, pKW would be the negative log of KW. We're going to see that in just a little bit. All right, so if I take the pOH, that means I'm going to take the negative log of my hydroxide concentration. All right, and if I do that, what I'm going to end up with is pOH, not pH. So be careful with this. If you have OH and you take the negative log of that, you're going to get pH. Now, one little way, I'm not going to show you the derivation here, but there is a connection between pH and pOH. Because as your pH goes up, your pOH scale is completely backwards. And this is confusing for a lot of students, and especially me. I don't like the pOH scale myself. But it's the opposite. 7 is still neutral, but on the pOH scale, if it's greater than 7, it's an acid. If it's lower than 7, it's a base. Because you're using an inverse scale. So as this one goes up, this one goes down. And they're connected together with this equation. All right, so this is given on the back of the periodic table. The reason I'm giving you this is that I might give you the pOH, and if I do, or if you have it in a problem you're doing, convert it to pH. Don't try to think through pOH. Really, guys, it's not worth your time and energy. Convert to the pH scale. Okay, so one last slide here, and then we're going to end, and I'll actually show you some calculations, so examples. Here's a list of all the useful equations that we've got so far. Kw is the equilibrium of water, and this establishes whether we have an acid or a base or not. Then we get to the pH and pOH scale. Again, be careful with using this one. I don't really like that one too much. I use it very sparingly. And then we got pH equals pK. Now that 14 is the negative log of pK. Now I'm not going to show you, but this equation here is connected to this equation. If you want to look up the derivation of it and see where this equation comes from, it comes from taking the negative log of both sides of this equation and deriving it. Now let's say that I have a pH equal to, well, no, let's do pH. Let's do hydrogen concentration. So let's say that the hydrogen concentration is equal to 3.42 times 10 to the negative 8 molar. Okay, what I want to know is what's pH, what's pOH, is it an acidic or is it basic? So what I'm going to do first is I'm going to find pH. pH is just the negative log of this number. So I'm going to take 3.42 times 10 to the minus 8. Okay, now based on the fact that I know pHs are close to this number up here, I know that my answer is going to be close to the 8. Okay, I know, because I've done this so many times, that the pH is going to be 7 point something. So let's see what that is. After plugging this into your calculator, what you should end up with is 3.466 and your pH. Okay, so there is my pH. Now, why did I take so many significant figures? One little rule, well, the rule for significant figures for dealing with pHs is you count it after the decimal. You don't count the 7. The 7 doesn't count in your significant figures. Since I have 3 significant figures here, I have 3 significant figures here. I wouldn't worry too much about this, guys. I'm not splitting that much, of a difference between significant figures. If you put 7.47 or 7.446, either way you're going to be okay. But just a little note that when I'm doing problems, you'll see me do that. 3 significant figures, you start counting after the decimal. So there's my pH, 7.466. Okay, so if you didn't do that, go get a calculator and make sure that you can get this number come out the way I have it. And again, I was close to that 8 because this isn't quite a 1.0 anymore. So I know that this, if I got a 3 or if I got 4 point something, I know that I made a mistake. So good idea to estimate it using that number up here. All right, so my pH is greater than 7. So therefore, do I have an acid or a base? It's going to be a base because my pH is slightly greater than 7. Greater than 7, I have a base. Less than 7, I have an acid. Also, I could compare this to the hydroxide if I wanted, or I can compare it back to neutral water. But why do that anymore? Let's compare this to 7 in our pH scale. It's going to be a lot more convenient. So if I want to figure out the hydroxide concentration, well, I already know how to do that. I can use Kw is equal to over my hydrogen concentration. Okay. Or what I could do is I could use this and say, well, 14 is equal to pH plus POH. Okay, make sure you make that P small. Don't make it a big P. It should be a little p. Okay, don't so it shouldn't be this. It should be, whoops, it should be that. So make sure you write it properly. Okay, so I could do is I could find my POH, which would be, as I just did right there. I should have made that better. Okay, so which would be 14 minus my pH. I could do that, and then once I get the POH, I could undo the log, and I'll show you that in class. I'll show you how to undo. No, you know what? Let's do it right now, just to make sure everybody has it on the video and all that. So let me show you what I'm talking about. Let's say that I have a pH. Let's go ahead and start with pH, and let's say that the pH is equal to 3.42. Acid or base? Acid, because it's lower than 7. All right, so I have this acidic solution. I want to know what's the concentration of the hydrogen ion. Okay, so what I have to do is I have to take pH is equal to negative log of the hydrogen ion concentration. So what I'm solving for is the hydrogen concentration. All right, on your calculator there is a button. First of all, let's remove this over here. Right, you got to get the negative onto this side. So I have negative pH is equal to the log of the concentration of the hydrogen ion. Okay, so don't forget this. A lot of students miss this negative. Don't lose the negative. Can't stress that enough. It's going to happen. I know it, but just don't do it. All right. I have to get rid of this log here. To do that, you want to find a button on your calculator, and it's almost always above the log. So you have that log button on your calculator. Well, right above that log button is a button 10 to the x power. Okay, that's what you're looking for, 10 to the x. That's going to undo the log, because remember, that is the log up there. So I'm going to do is I'm going to take 10 to the x of both sides. All right, so I'm going to take 10 to the x. So I get here 10 to the x, which in this case my x is the pH. And what that does is 10 to the power removes the log and leaves behind your hydrogen concentration. So this is the equation for finding hydrogen ion concentrations from the pH. I take 10 to the negative pH. Okay, 10 to the negative pH. So right here I'm going to take 10 to the negative 3.42. Plug that in my calculator and I can solve for my hydrogen concentration. So what would my exponential number be? It's going to be a 4 because of the fact that I have this number like this. So let's take a look. Let's do it on our calculators. Okay, so when I did it on my calculator, I ended up with 3.8, and I'm going to have two significant figures because remember, we don't count significant figures until after that decimal, right? We'd start after the decimal. Okay, so I have 3.8 times 10 to the minus 4. And since now I'm looking for molarity, because I'm looking for concentration, that would be my concentration. I'll show you that in class a little bit more. We'll definitely look at some examples in class to make sure you get this down. But that is how you go from pH to hydrogen concentration. One thing I forgot to mention earlier, by the way, is that your pH has no unit. There is no unit for pH, so don't put any units for pH. There's no molarities. It's a unitless value just like K. All right, that should be enough to get you started, and I'll see you guys in class to answer all your questions. See you later.